Welcome back to Chapter 3 of Principles of Mathematical Analysis. In this short but important section, we meet power series. A power series is an infinite sum built from powers of a complex variable z with fixed coefficients. These are the building blocks of analysis. The exponential function, the sine and cosine, and countless others are all defined by power series. Our central question is simple to state. For which values of z does the series converge? The answer is beautifully clean. There is a single number, r, the radius of convergence, computed directly from the coefficients by the root test. Inside a disk of radius, r, the series converges. Outside it diverges. Let's see how this works. Here is our plan. We start with motivation, recalling why power series matter and what question we are trying to answer. Then we give the formal definition of a power series and introduce the circle of convergence. Next comes the main theorem, which pins down the radius of convergence using the root test, together with its short proof. After that, we work through 5 examples that show every possible kind of behavior. Finally, we summarize the key ideas. Let's start with why these objects deserve a section of their own. Many of the most important functions in all of mathematics are not given by simple formulas. Instead, they are defined by power series. The exponential function shown on the slide is the prime example. It is literally defined as the infinite sum of z to the n over n factorial. The same is true of the sine, the cosine, and the logarithm. Next, let's see what makes a power series usable. But there is a catch. An infinite sum is only meaningful where it actually converges to a finite value. So before we can treat a power series as a function, we must know exactly which values of z make the series add up. For some series that is every z, for others only a few. Next, let's state the question precisely. This is the central question of the section, given the coefficients we see sub n, for which complex numbers z does the series of c sub n times z to the n converge. Remarkably, the answer has a very clean shape. The set of good z is essentially a disk in the complex plane, and its radius can be read straight off the coefficients. Let's make all of this precise. Here is the formal definition. We are handed a sequence of complex numbers c sub n. The coefficients, and z is a complex variable. The power series is the infinite sum, from n equals 0 to infinity, of c sub n times z to the n. Notice that the sum starts at n equals 0, so the very first term is just the constant c sub 0. We allow z to be complex, not merely real, because that is the natural setting in which this theory becomes clean and symmetric, as we will see in a moment. The key point, stated at the bottom of the slide, is that whether this series converges depends entirely on which z we plug in. The very same coefficients can give a series that converges for one choice of z and diverges for another. Next, let's picture the set of z where it converges. On the slide is the geometric picture that organizes everything. With every power series, we associate a circle in the complex plane, centered at the origin, called the circle of convergence. Its radius is r. In the diagram, the green shaded disk is where the series converges, the inside of the circle, while everything outside the dashed red circle is where it diverges. The orange arrow marks the radius r. Now, why should the good region be a perfect disk in the first place? The reason is simple but important. The size of each term, the absolute value of c sub e n times z to the echelon, equals the absolute value of c sub e n times the absolute value of z raised to the e n. So a term's magnitude depends on z only through its distance from the origin, never its direction. Convergence can therefore depend only on that distance, and that is exactly what carves out a circle. On the circle itself, the behavior is delicate and can go either way, so we leave that boundary case aside for now. At the extremes, the disk may have infinite radius, meaning convergence everywhere, or radius 0, meaning the origin only. Next, the theorem that computes R. Here is the main theorem, and it is wonderfully concrete. We form the quantity alpha, the limit superior of the n-th root of the absolute value of c sub n. Why the limit superior rather than an ordinary limit? Because the plane limit might fail to exist if the coefficients behave irregularly, but the limit superior always exists, so alpha is always well defined. Notice it depends only on the coefficients, not on z. Then r, the radius, is simply 1 over alpha. The conclusion matches the picture from before. The series converges whenever the absolute value of z is less than r, and diverges whenever it is greater. The remark handles the two extreme cases. If alpha is 0, we set r to plus infinity. So the series converges everywhere. If alpha is infinite, then r is 0, and the series converges only at the origin. Next comes the proof, which is just one line. The proof is a direct application of the root test from earlier in the chapter. We set a sub n equal to c sub n times z to the n, the actual terms of our series. The nth root of the absolute value of a sub n factors cleanly. The absolute value of z comes out as a constant, leaving the nth root of the absolute value of c sub n. Taking the limit superior turns that second factor into alpha, so the whole thing equals the absolute value of cz divided by r. The root test then says, converges when this quantity is below 1, diverges when it is above 1. Multiplying through by r gives exactly the statement of the theorem. The number r is called the radius of convergence. Next, let's see it in action. Our first example is the series with coefficients n to the n. Here the nth root of the absolute value of the coefficient is the nth root of n to the n, which is just n. As n grows, that runs off to infinity. So alpha is infinite and the radius r is 0. The meaning is that this power series converges only at the single point z equals 0 and nowhere else. The coefficients grow far too fast for any non-zero David to be tamed. Next, the opposite extreme. Now the opposite extreme. Take the coefficients to be 1 over n factorial. Here it is easier to use the ratio test than the root test. The ratio of consecutive terms is the absolute value of z divided by n plus 1, and for any fixed z that goes to 0 as n grows. A ratio with limit 0, which is below 1, means convergence for every single z. So the radius is infinite. This series is exactly the exponential function we met in the motivation. Next, the borderline case where the radius is 1. This is the plane geometric series, with all coefficients equal to 1. The nth root of 1 is 1, so alpha is 1 and the radius is 1. The new feature here is the behavior on the boundary circle, where the absolute value of z equals 1. There the series diverges at every point because the terms z to the n All have absolute value 1 and never shrink toward 0. Recall that a series whose terms do not go to 0 cannot converge. So on this circle, divergence is total. Next, a series that diverges at only one boundary point. Now divide by n. The nth root of 1 over n still tends to 1. So again the radius is 1. But the boundary behavior is now subtle and mixed. At the single point z equals 1, the series becomes the harmonic series, 1 plus 1, half plus 1, third, and so on, which diverges. Yet at every other point on the circle, the series actually converges. That last fact is not obvious. It will be proved later using a tool called summation by parts in Theorem 344. So here, the circle has exactly one bad point. Next, a series that behaves perfectly on the entire circle. Finally, divide by n squared. Once more the radius comes out to 1. But now the boundary is as nice as possible. The series converges at every point of the circle. The reason is the comparison test. When the absolute value of z is 1, the absolute value of the term z to the n over n squared is exactly 1 over n squared, and the sum of 1 over n squared is a convergent p-series. So absolute convergence holds all the way around the circle. Taken together, examples C, D, and E all share radius 1, yet show 3 completely different boundary stories. Next, let's see them side by side. Here are the 3 radius 1 examples side by side, each drawn as the unit circle in the complex plane. On the left, example sec, the plane geometric series. The whole circle is red because the series diverges at every point of the boundary. In the middle, example D, the series of z to the n over n. The circle is green, meaning it converges, except for one red dot at z equals 1, where it becomes the harmonic series and diverges. That is the single bad point. On the right, example E, with n squared in the denominator, the whole circle is green, so it converges everywhere. The lesson is striking. All 3 have exactly the same radius of convergence, 1, yet the behavior on the boundary tells 3 completely different stories. Next, let's summarize. Let's gather the key ideas. First, a power series is an infinite sum of coefficients c sub n times powers of a complex variable zeta. Second, and most importantly, the radius of convergence r is 1 over alpha, where alpha is the limit superior of the n the root of the absolute value of the coefficients. Inside the disk of radius r, the series converges. Outside it diverges. This number is read directly off the coefficients with no reference to z. Next, the part the theorem leaves open. Third, the theorem is silent about the boundary circle itself, where the absolute value of z equals r, and for good reason. Our 3 radius 1 examples showed every possibility. Divergence at all boundary points, divergence at just one point, and convergence everywhere on the circle. Settling these delicate boundary cases requires a new tool. That tool is summation by parts, the subject of the next section, which will let us prove the convergence claims we had to postpone. See you there.